Hi, my name is Tabitha Gunnars, and today I'll be presenting my master's thesis project on the visual field of the bottlenose dolphin, Tursiops truncatus, which was done under Dr. Jason Bruck's lab. So first, I'd like to go over the importance this research has and that it can contribute to improving certain methods that involve interacting with bottlenose dolphins, such as data tagging. And data tagging mainly consists of using these suction cups and attaching them to the dolphins in order to collect data on their acoustics, for example. And another method is using UASs, or unmanned aerial systems, which are known as drones as well. And these drones can be used to collect hormone samples from wild dolphins in order to assess their health. However, in order to do this, we need to address the gap of knowledge within the dolphin's field of vision, such as their blind spots. And so for this project, I'm assessing the bottlenose dolphins' overall visual field in order to determine where their blind spots are located in real time. Another reason of importance for this study is because past studies have claimed that there's a blind spot in the frontal area where the dolphin's rostrum is located, and that the dolphin uses their echolocation to compensate for vision in this area. And so I just wanted to test whether this was true or not, whether they did use echolocation or whether they do have a blind spot in that area. And I also wanted to take into consideration how unique the dolphin's eyes are, in that they can see both in underwater and in air. And this is due to these double slits that they have in their pupils that allows the admission of light to come through. But how does this affect their blind spot? Can it affect their blind spot? And so I feel like it's important to investigate this. And so the objective of this project was to establish the practical field of vision that takes into consideration the dolphin's perception and eye movement in real time in order to establish their functional blind spot. For the first part of the training, this consisted of using a Hoberman sphere, which you see here, where this little kid is standing inside of. And this sphere is able to contract and expand, and we used it in its expanded state. And we were able to attach these lights to these junction points all around the sphere. That way we could test the visual field of the bottlenose dolphin. But for this process, we did desensitization or habituation, and that mainly consisted of presenting the sphere to the dolphin until they were able to approach the sphere without hesitation, and that they were able to station themselves inside the sphere, and that they are responding in a positive manner. And that's what we were wanting for this first part of the training. In order to establish their overall field of vision, we use this Hoberman sphere to capture what the dolphins can see and what they cannot see. And so these LED lights were attached to these junction points, and there were 25 junction points, so 25 lights that we used, except only one light had batteries in it since the remote was capable of turning on all of the lights, and so we didn't want to overstimulate the dolphins in the study. The second part of the training was the LED light training, and for this we just basically transferred one SD, or a discriminative stimulus, to another. In this case, the SDs are the hand signal of the trainer and the light itself. And so the hand signal in these images are shown by the red arrow going in a downward motion. I just wanted to show you how the hand signal was conducted. And whenever the trainer does this hand signal, it is telling the dolphin to vocalize with a whistle. But we wanted to transfer this hand signal to the light whenever the light is turned on. And so when the light turns on, we wanted the dolphin to vocalize. And so I was able to partner up with Dolphin Quest in Bermuda due to Dr. Jason Bruck's long-standing research relationship with Dolphin Quest. And at this facility, we were able to use 3 subjects that consisted of a male and 2 females. And we identify them in this project as M1, F1, and F2. And you can see in the schematic right here, the different session locations. This is just where the experimental sessions took place. And right here in the bottom right corner is an overview of Dolphin Quest Bermuda. And you can see their outside habitat that they have and the facility. After successful desensitization or habituation, the dolphin was able to station inside the sphere for 30 seconds up to 2 minutes, and that was our goal in this study. So then we were able to attach the 25 lights to these junction points on the sphere. 2 of these lights were baseline lights, and that was just to begin and end the experimental session on a positive note. That way the dolphin's motivation was sustained at a good level during this whole session. And so the experimental session, we conducted it to where we tested 2 experimental lights between the baseline lights. And so we did this until all 25 lights were done once, and then we did all 25 lights again. And then we conducted it a third time if there was a yes response for the first round, for example, and then the second round there was a no response. And so we did it the third time in order to get a concise response from the dolphins. So as a result, we were able to find a minimum and maximum blind spot. And just to note, the gray area you'll see was not used throughout the study. And so for the minimum blind spot, you'll see this red area, and this is where all 3 dolphins had a no response. As for the maximum blind spot, the red area shown here is where any one of the dolphins had a no response. And we were able to conclude that bottlenose dolphins are capable of vision in front of their rostrum, despite these past studies stating that they use echolocation to compensate for their frontal vision. Now we can conclude that the blind spot occurs in the dorsomedial area of the bottlenose dolphin. That is this red area shown here in the image to the left. And we can also establish a field of vision. And you can see this green area is the area where the dolphin is, or all the dolphins were able to see. And so researchers can use this data in order to figure out where they should approach the dolphin, and that they should approach the dolphin from the rear with small fixed wing units in order to collect the samples that they are needing. So I would like to acknowledge the research assistantship I had through OK-LSAMP, the Bridge to the Doctorate program, and I'd like to give thanks to Dolphin Quest Bermuda because this project would not have been possible without their support, and I thank them for it. And then I would like to acknowledge my advisor, Dr. Jason Bruck, as well as my committee members, Dr. Charles Abramson, Dr. Donald French, and Dr. Matt Laverne, for their endless support throughout my master's, as well as Eric Abele, who was a master's student at Oklahoma State University, and he helped construct the 3-dimensional images. Thank you, and I hope you enjoyed my presentation.